So we looked at a power series that had the extreme of only converging at its center. Let's look at the reverse where it converges for everything. And this is actually the type of series we're interested in, power series wise, because remember I said the whole point of talking about power series is that these series representations of functions, that is our real goal in all this, writing sine, cosine, e to the x, natural log, all those things as power series is where we're headed. Well, if the series is going to represent the function, it'd be great if it could do it for all x values, right? Instead of just a few x values. And so it's really great when a power series will converge for all x, because that means its function and the series will match each other for all x. It'll be useful for all values of the domain. So let's look at this example, x to the n over n factorial. Again, our very first step will always be to not look at the original series, but to look at the series of the absolute value of the terms. That's so that we can use ratio or root. Remember, sometimes we lose track of why we're doing that step of the absolute value. It's because we'd love to do ratio or root, but those require, in the case of ratio, positive terms, and in the case of root, non-negative. And we don't know that because we don't know x. But in absolute value, then we're good. Right? So this series these a sub m are all strictly greater than 0 so long as we're not at our center, right? And that, again, we can always ignore the center because trivially we know every power series converges at its center. So ratio or root, well, again, we've got a factorial, so that pushes us towards ratio. So let's do the ratio test here. The limit as n goes to infinity of absolute value of x to the n plus 1 over n plus 1 factorial. There's our a sub n plus 1 over our a sub n. When we flip that, make it proper, something like that. As always, these guys cancel nice. We're just going to have absolute value of x there. These cancel nice. We'll just have an n plus 1 on the bottom. So I'm going to take that absolute value of x outside the limit because it doesn't involve n anymore. And now, no matter what x is, even the center, doesn't matter, for any value of x, this limit is 0, right? Because we know that this limit's 0 and it's just being multiplied by a constant. So 0 times any constant is 0, which is less than 1 for all x. So what does that tell us? That tells us that this series converges for all x by ratio test. But then ACT tells us that the original series converges for all x. So no matter what x you plug in here, there's an answer. This series is going to converge to some value. So thinking of this as a function, the domain of this function is all real numbers. And actually this one, as we will see when we look at Taylor series, this is an important series for us. It's actually the series representation of e to the x. And because of the fact that it converges for all x, this series representation for e to the x is good everywhere. For all x's, it does the job of converging to e to the x. So we will look at that. So this is really nice when a power series converges for all x, because if that power series is being used as a representation of a function, then so long as it converges to that function, we will be able to use it in place of that function. So that's really the three things that could possibly happen to a power series. You're either going to have some finite interval, like we saw, maybe of some radius, some finite radius, or a zero radius. When you have the single point, we just say the radius is 0. Or, in this case, all real numbers. And again, is there any conditional convergence? I guess I should emphasize that. It's absolutely, right? This is absolute convergence when we do this. This really is absolutely convergent for all x, so there's no conditional convergence. Again, there's no endpoints to check. That makes these cases really nice for analyzing, because once you get this, you're done. You know that series converges for everything, no endpoints to check. It's an infinite interval, so it's kind of odd, but we just say that the radius is infinity. When you have just a single point, just the center, we say the radius is 0. And if you have some finite interval, we say the radius is half that distance across. So yeah, really that's all you can have, is either a point, a finite interval, or everything.